Part 3, PCB photolithography method. I put title spin coating. Why spin coating? Because mostly we will talk about the thin film processes and UV exposure of that using photoresist. And a lot of our success depends on the spin coating. In the previous chapters, we looked at a mechanical PCB development process and find out that with hobbyist CNC machines it's not possible. You need a really professional one, and it's not the only shortcoming of this technology. Also, we should protect this copper layer when we build a prototype. We need additional such processes as solder mask and in some cases silk screening. Now, first, let's learn how PCBs are made in professional environment in a factory. Here is described the printed circuit board manufacturing process and what steps it includes. For rapid prototyping, we don't need all steps, we just choose what we need. But generally speaking, we should understand all process. Okay, first we design a PCB in CAD software, and we got all necessary layers out of this design. Then design reviewed, and we answer to engineering questions. There's a lot of things about the tolerance and other things. Then we're printing PCB design, typically with a laser and then film, photosensitive film. We get excellent quality. In the latest generation devices, I have seen even big high quality matrix with optical system that projects our design directly to photoresist without film. But it's advanced method, and definitely we are not able to use it in-house. Then printing copper for interior layers, for multi-layer boards, I know, from 4 up to 8 layers. There are additional process. Etch internal inner layers or core to remove copper. Then we align layers. Then we do automatic optical inspection. It's a high precision process. And then we put together all those internal layers based on a precise alignment and make a, let's say, one big sandwich of our PCB. When it's done, we do the drilling, and then it's chemical process, PCB plating. We put this in some chemicals, and this chemical process is adding copper to the drilled holes. Then we do outer layer imagining, outer layer etching, outer layer automatic optical inspection. Then we apply solder mask to protect the copper layers. Then we apply silk screen, some prints that makes easy to work with a PCB, because we have some legends on it, and finishing PCB. Do the electrical reliability test. It's so-called flying probe or automatic probe that goes and tests continuity of each track. And then we cut out from the big board our board size. Then quality checked, visual inspections when needed, and packaging and delivery. This is professional manufacturing process. If you want, you can read it more on our web. But generally, there are 20 steps, and in-house for prototyping, definitely we do design the PCB, design reviews and engineering questions, of course. Printing the PCB designs, yes, yeah, we are printing film, or putting it in a files for CNC router. Practically, we never make a multi-layer boards. We always, when we need a multi-layer boards, then we order them in a factories. Step 5, 6, 7, 8, we skip. Of course, we do drilling, and we can do drilling with hobbyist CNC machines. Typically, for in-house PCB prototyping, we don't do PCB plating, we just solder vias from both sides, and that's it. We do outer layer imagining, we do outer layer etching, outer layer automatic optical inspection we replace with just looking at the microscope our result. Solder mask applications, yes, it's easy and we do it. Seal screen case by case for prototypes when you're working just with one. It is nice to have, but we can live without it. It's by far more difficult to live without solder mask application, because the solder mask simplifies your board soldering very much, and it is worth to do it if you have a proper easy process how to apply it. Electrical reliability tests we don't do, we just put it together and test the board. Profiling and route out, yes, we can do it in-house with a simple hobbyist machine. Quality check and visual inspection, we are building board, engineer is building board, and this is not a mass production. It is going on a fly. Packaging and delivery, we are not delivering anything, we built a prototype and that's it. And now let's look to dry film imagining of PCB. This is important, it's more important than the previous introduction of PCB manufacturing process. That was just more for educational purposes, but this is what I want to do. And after researching many documents and even books, I find on a PCBWay blog perfect summary, one pager I would say, what explains key moments how to do PCBs with a photoresistive method. If you're aware about it, skip it. But for me, who is engineer, and in general I understood all process but never use it in a practice, I found out this document valuable. First, those are not amateurs. Those are PCBWay is a professional PCB manufacturer. Engineer who wrote it, each sentence is correct, absolutely correct. And if you are about a process, skip this chapter. But for those who are not aware, and I know that many new generation people are not comfortable with focusing for a longer time to some topic, but it is important. So I will go through this document, and I decided that I will read it item by item, this document. If you don't want, don't follow. But if you want to build in-house PCBs, it's important to align our knowledge with the professionals who wrote a document. Sometimes we are doing small things in a wrong way, and it's impacting our final product quality. The process is very important. Okay. This is dedicated to dry film imagining for PCB. The similar process is for liquid photoresist method, but dry film becoming more and more affordable for DIY community, and we will focus on it. The photopolymerization characteristics and convenience of dry film photoresist make it useful for image transfer in PCB fabrication. Ideally, the dry film imaging process should be done in a clean room with amber light illumination. Dust is killer in fine line constructions, hence a clean room is needed for PCB fabrication with fine line structure. For example, class 10,000 clean room can be used up to 5 mil or 0.127 millimeters line width. This is very important sentence. Of course, in office environment we don't have a clean room, but through the process we can do all possible things that keep dust at minimum. Yeah, and it is critically important. I also find out when I did experiments, sometimes you have excellent board, but in one place there was a small dust piece and the fine track is cutted out. No, you could live with that, but dust really is a key challenge for DIY PCB fabrications or for in-house prototyping. Okay, dry film is viable in range of film thickness from 1 to 2 mils. Remember, it's mils, it's thousandths of inch. For fine line resolution, thin film is desirable. Thick film is more suitable for hole tenting is needed. If you want to precise PCB, you should really be able to make a thin film. And there are several processes how to do it. We will look at them further. But thickness of film is critical. Dry film, how it looks like, they are constructed in a 3-layer sandwich structure. A layer of photopolymer resist sandwich by a bottom layer of polyethylene film acts as a separator, and the top layer of polyester or Muller film acts as a protector. There are 2 types of films protects that thin layer of photoresist. In addition to protection, the top plastic film also functions as oxygen blocking layer to limit the amount of oxygen migrating into the resist film during exposure. Important, another advantage. During lamination, the laminator will remove the bottom film. The top film should remain in contact with photoresist for at least 15 minutes after exposure. That means if you do exposure, you leave it for 15 minutes to finish this photochemical process, and only then you go for developer. It should be removed just before developing. The dry film is sensitive to long wavelengths UV radiation in UVA range. Different brand names have slightly different configurations. Okay. For production type quantities, it is common to use roller coating process or wet process to replace the dry film process. Actually, those processes are the same, different method how you apply photoresist to laminated PCB. In wet process, liquid photoresist is transferred onto copper clad by roller and dry in a clean environment. Again, clean environment. Drying temperature of 50 degrees for 10 minutes. Very important. Actually, those who work either spray some photoresist or do another coating of photoresist, you should dry it in a high temperature at 50 degrees. You need some kind of oven for 10 minutes. And then it has a very good adhesion and not losing any abilities to create a good PCB. Comparing with image transfer process using dry film, this process is inefficient for small quantity because handling a high setup costs. Dry film normally gives a better result than wet process because of better control in the thickness of photoresist. It is more difficult to control thickness of photoresist using roller coating in a PCB workshop environment. Although the requirements of single-sided board is usually less stringent than double-sided boards in terms of wider traces or lower density, dry film process is recommended for image transfer. In a production environment, dry film is normally reserved for higher tolerance board because the unit cost is more expensive. So here you have also answers dry film versus liquid photoresist. Generally speaking, it's the same. But you need a laminator. Definitely you will not have it like a production type or some expensive one. You should laminate it with some adapted devices. And since you are not working in a sterile environment, in a clean room, typically often you get some bubbles or wrinkles in this lamination process. And a lot of your success depends on lamination process. But dry film is very good process. And the third, there are also positive acting photoresist coatings available in the market. Before we talk with a negative photoresist. For positive resists, exposure to the UV light changes the chemical structure of the resist, such as become more soluble in developer. For exposure, resist can be washed away by the developer solution exposure the underlying metal for etching. So, but I will not drill down here because we will use, and normally we are using only negative photoresist. Surface preparation, super important topic. Often DIY people has a shortcuts here, but it is critically important to prepare surface. After matching, the PCB must be cleaned and scrubbed, sandpaper or industrial type scrub pads such as blah 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 from 3M. Alternatively, a brushing machine can be employed to remove the dirt and oxide before lamination. Forget about it, we don't have it. Very important, it is desirable to immersion the PCB in a 10 to 15 sulfuric acid. I will check how to pronounce it.
Sulfuric acid. Sulfuric acid.
For 1 minute to give a better surface preparation. It becomes kind of uneven and adhesion is much better. This is a dangerous process for your... first you should create this sulfuric acid 10 to 15% liquid. You should store it, and if it hits your clothes, there will be some hole in it. I am not doing this process. I try to avoid any nasty stuff in my environment, but it helps a lot if you really want to have a high quality PCB. Okay, dry film lamination process. I think you can find a lot of information about it. There are a number of DI people who are using paper laminators, successfully using that. You can also use just hot iron to make it. Watch videos. It's not today's topic for me to educate someone how to do this lamination process. Tons of videos in a YouTube. Contact exposure. After the dry film laminated PCB is cooled down. Important, it should be cooled down. Sometimes when you speed up a process, it's still hot and it's a problem. You should really cool it down to the room temperature. It's ready for imaging. Okay, dry film polymer is sensitive to UV radiation around 350 nanometers to 400 nanometers. And you can easily work with amber yellow lights to minimize UV radiation. I'm working in an office with the LED lights of 3000 kelvins. It's yellow lights. You can even get to 2007 kelvins, absolutely without problem. So it's easy requirements how you can do it. Okay, equipment used to contact exposure is normally composed in a vacuum. What is here is important, that you really need to press film to photoresist, really with a force. So to hold the photo tool in close contact with PCB and collimating UV source. In addition, a timer is needed to control the exposure time of the photoresist, and you need to do those number of experiments until you find the optimum settings. Those are critical. You should write it down and really use a timer. Exposure time is function of intensity of UV radiation. That is function of irradiation source. So there's many variables. Variable how far is the UV source from your device. Exposure time, and then to find all those parameters, write it down, and then you can repeat it with confidence. For perfect exposure, industrial type exposure equipment uses high intensity UV light source composed by a number of mercury arc lamps together with optical system to generate an intense collimated and uniform UV light to achieve reliable and quality image transfer. What is here important? Use a high intensity UV light source. I saw in YouTube and many DIs use a really weak source, and exposure times are up to 10 minutes. Not good. It's the same for outdoor exposure. You can do it, but it's better than you have something between 5 to 30 seconds of exposure needed. That means high intensity UV light source. In particularly, good contact between photo tool and PCB can be achieved by placing the workpiece inside vacuum chamber and hold them together with a mechanical press. A highly collimating source is essential to achieve straight edges and fine line formation. Collimating probably means parallel, maybe. It's not word what I understand. Here's one of equipment for exposure. As I mentioned, exposure time can be determined experimentally. We can prepare a number of PCB stripes and expose it using the step transmission wedge. This is how I did it. At the beginning, when I set up my exposure unit, I have no clue either those are minutes, tenths of seconds, or few seconds. And I find out I started with a maximum 1 minute exposure and come down that 15 seconds is kind of optimum for my setup. 15 seconds is great. But I spent about 8 hours trying to find that optimum setup. You need to do experiments. You should have several PCBs. You should do that development of those and then find out which one is good, and then you go with some test patterns with the fine details and inspect them under the microscope until you find a sweet point of your exposure. It's very important, especially on a DIY environment. You can't make very, very dark films. It's a problem. You can print with a printer, and that means your window of optimum exposure is narrow. If you use real photo film, when a black is black and transparent is transparent, it's much easier. But in home or in DIY or in a prototyping, non-professional prototyping environment, it's you have pretty narrow window to find this optimum exposure timing. Development and striping. Here we're working with the chemicals, and this is very good document because everything is put in short sentences and given right values. Actually, I find in internet some other proportions, and those are kind of recommended. But here, what professionals are saying. This is how they prepare their internal environment for development, to achieve the maximum precision of PCB. For negative photoresist, developer can be made up with 0.85% with water, 8.5 grams per liter of sodium carbonate anhydrous. Jesus. I'm not a chemical guy, especially in English. Sorry, those who knows, I will look how to pronounce it and maybe repeat it properly.
Carbonate anhydrous.
Carbonate anhydrous. Jesus. It is, I think, caustic soda. Actually, you can find it as a washing powder type somewhere. It's easy to buy, and it's environmentally friendly. You can splash it in the toilet afterwards. It's a kind of soapy stuff. And another one is 1% of water, or 9.9 grams per liter of sodium carbonate monohydrate. Some variation of this caustic soda. Yeah. And 1% by water of potassium carbonate. Probably not that easy to get, but anyway. So 3 types of developers. All of them are human friendly. They are not toxic, and they are not dangerous. Development of dry film can be done by immersion of spraying with a spray pressure. Typically we don't have a spray pressure machine, but we can gently brush it with the fingers or with some brush or some painting roller. And any of this method is perfect. I tried them, they work well. But this is industrial. Then you have bars, and then you have some parameters, how intense should be that spraying. This is how it is done in a factory, and and describe it in a physical parameters. You can repeat it. Also temperature, room temperature, a little bit warm, little bit 27 to 35 degrees. And the last is striping the dry film. After you do etching with a 3% by sodium hydroxide at 55 degrees Celsius, also to spraying. But the sodium hydroxide actually is a pipe cleaner. It costs 8 euros per liter in Home Depot, and you can read those very small letters and find out that that formula, it is in high concentration, it is dangerous because you can get skin burns, but it's for a home usage just, but 3% it's absolutely nothing, no problem. Also you can splash it in a toilet afterwards. It's meant for that. Pipe cleaner. Okay, what we are missing? We are missing etching chemicals, and I will leave it for the later one, because there are several options, but 2 of them are human friendly. So I know that it may be boring, but it's very important that you clearly understand the process and use it as it's described. I find out that many DIY people or some electronic enthusiasts think that you can skip some important steps like prepare the surface. Yeah, it is important to prepare the surface because all your tolerance depends how well this photoresist sticks on your board, and you should do it in the right way. You should do it in the right way. Read it, repeat it. Also about dust, it's very important, and some of my result problems was directly connected with the dust. Yeah, some tiny tracks were cut due to the small dust on a board. Yeah, but for prototyping you can live with it, you can fix it, and no problem.